lecture in the Professor Krishnamoorthy Endowment, HSC 2023, the Dr. comments. As speaker, Dr. Narayanan C. Viswanath, Associate Professor in Mathematics, Govt Engineering College, Thrissur, Kerala. The topic of the lecture is Transient Solution of Elthuruth and Mathematical Change using homotopy perturbation method. This is on behalf of the committee, Endowment Trust, Department of Mathematics, and all of us here. Welcome the speaker.
So I thank the organizers for inviting me here. The topic that I will be presenting today is transient solution of conditional markers using homotopy perturbation method. So this method is used for sorting both linear and non-linear differential equations. And this is a semi-analytical method. Therefore, the solution can be obtained as a function rather than a number. So this method was introduced by Prof. J. through his papers in the year of 1999 and 2000. Now, PhD has received around 4,000 citations according to Govt, and according to Science Direct, it is around 2,500. So that shows how good is this method in an application point of view. Now, Viswanath 2022 introduced this method to the field of knowing theory. Before that, this method was introduced in the theory of birth processes in a few papers. So, I will discuss the application of this method in the transient study of some 2D models. So, I will first discuss this method. So, consider a differential equation of this form, where A is a differential operator, PZP is the unknown function that we wish to determine, and FZP is a non-analytic function. So the method is to assume this operator A as a function of two operators L and L, where L is a simple probably the linear part of A, and N is the non-linear part of the operator A. Now, a homotopy is constructed as phi set dq as a power set is in a new variable q. So the q is a new variable that we are introducing. So here the coefficients of the power series q are functions rather than numbers. Now we substitute this to form the homotopy equation as given there. So you can see that when q is equal to 1, when q is equal to 1, we can combine these two. So this becomes n plus n, then q is 1, and that is A. And when q is 1, these two terms get cancelled, and one can see that this is nothing but this differential equation. This one perturbed a little bit using the variable q, and therefore phi set t1 is a solution of the differential equation. The top one, A set t minus F4 set t equal to 0. So this is the idea of the method. So when q is equal to 1,
You can see that phi set T1 is a sum u0 plus u1 plus u2 plus etc.
that gives a feeling of a Picard iteration method of solving a differential equation. But these two are entirely different methods. The homotopy method is maybe a little bit more general. Now, as q changes from 0 to 1, phi set tq. So when q is 0, what happens is that this will be absent, so that the differential equation is n of this equal to. So the differential equation reduces to a simple form, maybe the linear form when q is equal to 0. So we start from q equal to 0, and when q changes from 0 to 1, phi set tq changes from the initial plus u0 to the final solution or the real solution p set. So that is p set t equal to phi set t1, which is a sum of u0 u1 x. Now we will study the differential equation that is satisfied by the infinitesimal generator of a Markov chain. So that is given by dy dt of pt equal to pt multiplied by q, where pt is a raw vector that represents the probabilities of states in the Markov chain. The initial condition is that p of 0 equal to alpha, and by the initial probability vector. Here you can say that f of t is equal to 0. That is this one, that analytic function f set t. So here there is only one variable, z is not a variable here. So ft can be seen to be equal to 0. So here we split the a into two parts, n plus n. So where n is the linear part, dy dt of pt, that has that definition, and the nonlinear part is defined as minus n of pt is equal to minus pt multiplied by q. So with that definition, we will transfer the differential equation, the top one, into a homotopy equation which has this form. Now phi tq is a power series in q, so we substitute for phi tq and collect the coefficient of similar powers of q and equate them to 0. So that gives a relation between the variables u0, u1, etc. So that is the trick of this method. So the initial this is one of the most important steps in this method to make an initial guess. For example, this is the easiest way of guessing what is pt. Because pt as alpha. So remember that alpha is p of 0. So initially p of t will be very close to alpha, but then the picture may change as time progresses. So with this definition as pt equal to alpha, this equation that the d by dt will vanish because u0 is independent of t, and therefore this will vanish. This one also will vanish, and we will get a simple differential equation with this easy guess, and that is given that d by dt of phi tq equal to q multiplied by that one. Now, what we do, we compare the coefficients of similar powers of q on both sides. That gives some differential equations of this form, which can be solved iteratively, giving uit as alpha ut power I divided by I factorial.
Now, PT is the solution is equal to 5 to That's something when Q becomes equal to 1. So 5 to 1, if you remember, 5 to 1 is U0 plus U1 plus etc. And when we substitute for Uy as this, we can say that the solution is alpha into the power Q2, which is the solution of the differential equation that we so here d by dt of pt equal to pt multiplied by q. So we find out that the general solution of a continuous time molecule chain can be obtained using this HBM method. Now we will discuss whether we can obtain the uniformization method, which is a semi-analytic method, semi-analytic solution of the differential equation that we saw earlier, that is given by alpha multiplied by summation e to the power minus lambda t power n by n factorial multiplied by p raised to n. The p is a stochastic matrix that is given as this p equal to I plus q by lambda, where lambda has this definition. Now again we split the operator, differential operator as d by dt of pt plus lambda times dt. So you can say that there is a change in the definition of L. Earlier the definition was this L pt equal to d by dt of pt. Now we are taking an additional term. This one is the additional one, and here also there is a change in the definition. It is defined as minus lambda pt q. Earlier it was a little bit different. So the homotopy equation becomes takes this form. Now the question is, what is our initial guess? So we have changed the definition of L. So we change the initial guess also as alpha e to the power minus lambda t. Earlier it was just alpha, which is it was independent of time. Now we are assuming that it is alpha e to the power minus lambda t. So what is the intuition behind this assumption? Okay, when t equal to 0, p of 0 is alpha. So initially the probabilities are according to alpha, and then as time progresses, this relevance of alpha that fades out, and probably the molecule chain may convert into its steady state. So the relevance of the initial distribution that fades out. So that is the intuition behind taking U0 as alpha e to the power minus lambda. Now when we substitute that in the equation above, by taking U0 as this, again we will see that these term vanishes. This differential equation vanishes because alpha is to minus lambda t is a solution of this differential equation. This part here. So that vanishes, as well as this one also vanishes. So we will get a similar differential equation as in the previous case that gives rise to this system of equations. But this one was different from what we obtained earlier. Earlier it was just d by dt of uyt equal to ui minus 1t cube. But now it is a linear differential equation of this form. But one can easily solve this differential equation by taking the integrating factor, etc. And the solution is given by this. Uyt's are iteratively solved as alpha e raised minus lambda t, that one. And pt is the sum of these probabilities, sum of these functions, and hence pt has that form, which is nothing but the uniformization solution. Okay. Okay, so the uniformization solution can be obtained from HBM method. So now we try to modify the initial guess so that a better method, in some sense, a better method than the uniformization may emerge. So what should be the initial guess of U0? See, here we guess the U0 t as alpha elevation minus lambda. So as time progresses, its relevance of the initial distribution fades out, but then there comes the steady state probability vector. As time progresses, the probability weighting tends to the steady state. So why not bring the steady state also into the picture? So with that in mind, we will make our initial guess, we'll change our initial guess as alpha elevation minus lambda t plus 5, which is the steady state probability vector, 5 multiplied by 1 minus elevation minus lambda. So here we assume that steady state vector exists. Only in that case, this can succeed. Now, there is a change in the differential equation. Because of this assumption, we will be getting some terms like this, additional terms, which was in there with the earlier guess. And therefore, there is a change in the differential equation also. This one, there is a change in the first differential equation that U1t satisfies, but that can also be solved.
So if we change the option of U1t, then we will reach another set of solutions.
Yes, probably.
And then the convergence is also there.
Yes, convergence will be calculated using the measurement. Okay, then recursively solving it with UIT. So earlier it was just this term, but now an additional term like this comes into the picture. And PT is the sum of these UITs, and that is equal to this. But you can see that these are the Poisson probabilities, and here we are summing all the Poisson probabilities, and therefore the answer is 1. And therefore this is just minus 5. And plus pi is here, so there gets cancelled. So this is nothing new. This is the uniformization method itself. So what is new in this method? See, this method can be different from the uniformization method if we truncate the definition of PT. Okay, in practice, when we evaluate the infinite sum, we truncate it at some level n. So when we truncate it, these two are different. This is different from 1, and therefore there will be an additional term coming into the picture. Now, do we have something similar to this in the literature? Here is one reference by Dept in 1993. Their formula is this thing here. Something similar to this, but instead of pi, they have taken the vector Vk, which is obtained from the. So as k tends to infinity, Vk becomes the steady state probability pi. So when k is large, both these formulas are the same. But when k is small, they can be different. So in that paper also, Dept discusses about the convergence and other issues related to this one. So the point is, using the homotopy perturbation method by suitably manipulating the definition of L and the initial guess, new methods can be found. So now we will study some queuing models. using this method. So here is an SS inventory model with the random data. So what happens here is that we have S inventory items where customers arrive according to a Gaussian process with parameter lambda, and there is no service time, so immediately the customers are served. And the reordering happens at the rate mu when the system, the inventory size falls below little order is placed and it gets realized at the rate mu. So this is the graphical representation of the SS inventory model. Now the Chapman-Kolmogorov equations corresponding to the probabilities PJT, this probability is ID equal to J, they are given in this fashion. Now we attempt to solve this system using the perturbation method, homotopy perturbation method. But then here there are several variables, P0 dash PB, PJ, etc. up to PS. So S plus 1 functions are there, S plus 1 differential equations are there. So we must write this system as a metric system. P dash B equal to Pt multiplied by Q, where Pt can be partitioned in terms of the states as P0 T, P1 T, etc. Pst. Now L and N need to be defined. So that are defined in that fashion. dy by dt of Pt is L and N of Pt is minus Pt Q. Now here we have to define S plus 1 homotopies. So phi j dq, the variable Q is taken as the same, and using the same variable we define S plus 1 homotopies phi j dq. Now PJT is giving the Q times 1 phi j dq, that is summation I equal to 0 to infinity uijt. Now since we have S plus 1 such homotopies, we combine them into a vector given by phi 1 dq, phi 1 dq, etc. Therefore, that vector homotopy phi dq that can be represented using UITs, partitioned as UY0, UY1, etc. So we take the initial guess U0 as a constant one, because that is the most easiest one to make, so that we will have a nice form like this one, and the comparison of the coefficients of Q gives this set of equations. Phi t2 are substituted as. Now compare the coefficients of similar powers of Q. We will get a system of equations of this form ui dash t equal to ui minus 20 Q. Now you can see that this is similar to what we had earlier. Similar to this thing, p dash t equal to pt multiplied by Q. Okay. But the advantage here is that one can solve this recursive. But the challenge is that we cannot solve it manually. That is the challenge here. Because a lot of integrations need to be performed. So nowadays we have several softwares that compute symbols, that perform symbolic integration very fast. So we depend on such softwares like MATLAB, that is the one that I use, for solving this system of equations using symbolic integration. And that system, when expanded, will look like this. This can be solved. So that is why I said manually solving this. You cannot take about that manually solve such a system of equations. Now the initial condition is assumed as that, and the solution Pj can be obtained as summation I equal to 0 to Yj. Now we extend this model. So in the earlier model there wasn't any backlogs. So when there is no inventory available, a customer arriving at a stage is considered to be lost. But here we will consider keeping backlogs, and therefore we have an infinite dimensional system, and therefore an infinite dimensional system of equations to solve. And therefore, to solve those PIJTs, we will take the help of generative functions. So Pj set t is a generative function. So an additional variable set comes into the picture. So there are s plus 1 such generative functions. But the procedure from here is the same as before. That is, we will assume that there is a homotopy corresponding to each Pj set t, which converges to the solution Pj set t as q tends to 1. So this is the system of differential equations that is satisfied by the generative functions. And we define the homotopies Pj set t as summation I equal to 0 to infinity Qij set t. Repeating the procedure in the previous problem and comparing the coefficients of q on both sides, that gives the set of differential equations in this form, which can be iteratively solved to obtain a semi-analytic solution. But here the challenge is that we will get a solution in terms of two variables z and t, and the probabilities are coefficients of z. So we have to, if we wish to obtain the probabilities, we have to arrange the coefficients, we have to arrange the solution as powers of z. But there is also a provision for that. One can arrange the solution in such a way that it will look like a power series in the variable z. Again, the problem, the challenge here is that time required for these things is very huge. Therefore, there is no comparison between this method and a numerical or semi-analytic method like the uniformization method. There is no comparison in terms of time. So, computationally, this method cannot be said to be computationally feasible as it stands, but when the computational power increases, this can definitely be a good method, because then one has the freedom to assume the initial solution as different from the constant one that we have taken. Maybe we can take more general functions as the initial test, and then we can get more efficient solutions of the system. Now these are some simulations that we have done to check the accuracy of the method. You can see that up to time 25 we have given the result, and that agrees with the exact value of probabilities. So this can definitely be performed, but the time can be very huge. Now another model, what is the difference between this and the previous one is that here there are three coordinates. So n is a finite number, n is a finite number, x also finite, and y. which is a handoff process, patient handoff process in emergency departments, where only knows the patients who needs transfer from one cell to another cell, or one department to another department. And there are some assumptions regarding the arrival and service process. Graphical representation is also that this model is due to Su et al. 2020. So this diagram is taken from their paper. And they conclude that they couldn't obtain the transient solution except in some very special case. So we attempt whether this can be obtained using the homotopy perturbation method. So defining the homotopies as Pn xyt as summation I equal to 0 to infinity u in xyt. You see that a system of differential equation emerges which can be iteratively solved to obtain the solution. There are some references. Then I will stop. Give our questions, please.
Poisson distribution, time varying distribution in the initial slide. That is it first appearing. Yeah. So is it something your choice or it is a part of?
Sir, this is due to the uniformization method, due to Viswanath and others.
So what will happen if instead you go for some other distribution within that?
Yes, such methods exist. For example, Erlang process that one can use, but then the simplicity will be lost, and we cannot expect the semi-amenity in such situation.
Regarding the initial condition, you were mentioning that some additional things we can utilize the method of but then will it guarantee that you get a better improved solution? For example, in a method in the computation of R, the R matrix, you start with R0 equal to 0, and then why it is to be 0 rather than some other number. The answer Ratush gave long ago was that you may not even able to get and there will be probably some divergence, they don't even converge. The convergence problem will arise.
Yeah, it may arise in some cases, but in most of the cases we will get the convergence. So there's a proof in the original paper that guarantees the convergence of the solution.
But under some conditions.
Yes, but the conditions are very
there are not very interesting.
very general conditions. So, the failure is several possibilities can be thought. Like here, we can think about a change here in the definition of L, and then change the initial, take the initial this one. So that will give another possible solution, different from the solution that we obtained here. So this is what we obtained here, but this is same as the uniformization solution. But when we truncate this, these are different solutions. So that similar solution is due to CR2 vector, but their method is very different. So something similar may be achieved using the model. So here the advantage is that we can think about several variations. Now I checked whether this is a valid expression and found out that this is much better than this alone. Especially when n is small. When n is large, then there is no difference. Because when n is large, this will get cancelled. Minus pi n plus pi, that will get cancelled. So when n is small, there is a difference. Then this is more close to the solution.
Maybe it's looking like some error path.
Yes.
Some disturbance as in stochastic verifications.
Maybe a correction path. This is. Something is missing here, but that can be substituted from the something like that.
About the dimension, when you move to 3 dimension, you find there is some tumbling block. You have a 2 dimension, 3 dimension data.
Not here, so you can address the number of software. ഏത് ഡയറക്ഷനാണ് ചെയ്യാം, പക്ഷെ സമയം കുറേ കമ്പ്യൂട്ടേഷനിൽ ഇപ്പോഴത്തെ സ്പീഡ് വെച്ചിട്ട് നോക്കുമ്പോൾ ഭയങ്കര സമയം.
So here the selection of the initial solution is very important. So we need to have some clue regarding how the solution is going to behave.
Yes.
But if we say model which doesn't have any clue regarding the behavior of the solution, then how will it proceed?
Yeah, but we have the initial cognitive that will be there in any case. So one chance is that we can take the initial test as alpha. Another is alpha e to the minus lambda, and then combining a steady state. If the steady state is not possible, then we have to take alpha e to minus lambda. But then other options also we need to check. And I have done so.
Being an initial value problem, maybe the system has many solutions. That is why if you select one particular unit, you will get one set of solution for another. You can
But the solution is the same. Solution must be the same.
No, we are putting units zero equal to something like that.
Yes.
So it means that you are expressing the same solution in different manner.
Yes. Same solution in different manner. So that is the strength of the method.
In the initial value problem, there are many more than solutions. There is a chance.
No, but under some conditions, so we are discussing Markov check, so solution is unique.
വീണ്ടും നല്ല വളരെ രസകരമായിട്ടുള്ള ഒരു താമസിന് മനസ്സിലാകില്ല. Somebody else will translate what I am telling in Malayalam to you. രസകരമായിട്ടുള്ള ഒരു മെത്തേഡ് സ്റ്റൊക്കാസ്റ്റിക് മോഡലിംഗ് പ്രോബ്ലത്തിൽ സോൾവ് ചെയ്യാവുന്നത്. ഇപ്പോഴത്തെ ഒരു ഡയമെൻഷൻ്റെ പ്രശ്നമായിട്ടാണ് ശ്രീമതി പറഞ്ഞത്. ഒരു പക്ഷേ വിത്ത് ഇംപ്രൂവ്ഡ് സോഫ്റ്റ്വെയർ തിങ്സ് മേ ഇംപ്രൂവ്. ഇപ്പോൾ വളരെ നല്ല ഒരു പ്രസൻറ്റേഷനാണ് ശ്രീനിവാസൻ നടത്തി. രാവിലെ നമ്മൾ നല്ല രസകരമായിട്ടുള്ളൊരു രണ്ടുപേർക്കും പ്രത്യേകം അഭിനന്ദനങ്ങളും. വീണ്ടും നല്ല തലത്തിലോട്ട് ഗവേഷണങ്ങൾ നടത്താൻ സാധിക്കട്ടെ എന്നും ആത്മാർത്ഥമായിട്ട് ആഗ്രഹിച്ചുകൊണ്ടും നന്ദി പറഞ്ഞു. ഇത്രയും കേട്ട് കഴിഞ്ഞാൽ ബേസിക് റെപ്രസെന്റേഷൻ എന്ന വാക്ക് approximation. Given a distribution, how to predict the one, for example, only non-negative property only line. So zero infinity. I am considering the non-negative property distribution or defining continuous distribution. Continuous distribution or start with a random variable x. Yes, a distribution function, error distribution. For this is on the non-negative part of the data. So G means due to mean, for example, G of t equal to probability that x is less than or equal to t. So keep non-negative. Our industry is fine. And no specific form is given rather it will be difficult to find. It is impossible to find their percentage, basic percentage. But then, given the form, how to find out a basic representation for that particular distribution? Basic representation would mean we write pH for free state. representation would mean that when I'm just continuing the lecture where I should not say where we concluded because during the talk he mentioned that we phase state representation. So there is an initial probability vector. So basically there is a finite state space marker chain and a transition probability vector is for the marker chain. But then what I consider is a continuous state situation and therefore I consider the infinitesimal generator of the marker chain. That means whatever happens in a short interval of duration, let us call it H. The changes that take place in a short interval of duration H. That we call the infinitesimal rate. All those values. So I will introduce the states in the Markov chain. Suppose we label the state space of the Markov chain as 1 to m and m plus 1. This m plus 1 is what is called an absorbed state. And these states are transient, which means Markov chains states in these states only for a finite duration of time. It can be very long. When can it be long? That also can be actually identified from this scheme. And then what is the meaning of it staying there for a very large amount of time? And then what is the connection between the invertibility of T? And if it is not invertible, how it leads to non-invertibility? Such questions also can be answered very easily. So I will give an approximate idea about that. Now this T is, so we have the Markov chain. Now this is the initial probability vector, but restricted to this path. So alpha 1, so alpha, this corresponds to this, there is a probability alpha m, which means we have m plus 1 elements. We randomly pick an element from this to identify the state where we should start. And if it is m plus 1, well, it is absorbing and therefore it does not move out of that. If it is transient, and then it just moves around the transient states or directly gets into. Therefore, I pick a direct element of the state space in the transient part, and then it may directly move to m plus 1, or it may move to another state J, which is a transient state, and then move to m plus 1, or it may just go around all these things, not necessarily all of them. Several times and finally get absorbed. The time until absorption to this, suppose I designate it by U. So this time until absorption to this state m plus 1, that is referred to as phase state distribution. Now there is a very important property for the transitions among the transient states. This certain time in any state, suppose it is in state I, that is long, then it can move to state J, after an exponentially distributed amount of time. So it stays in the state I for an exponentially distributed amount of time before transition to J. And then when you have an exponential distribution, actually you should have a parameter, a single parameter is involved there. For example, the exponential distribution has the form lambda equal minus lambda t, where lambda is positive, t is non-negative. This is exponential density. So this is the form of the Sojourn time density. But then what happens is this parameter lambda will be depending on the state in which it is in and the state to be visited next. That means the parameter now we designate as lambda ij. So this T matrix is this one. And then suppose I just add another thing along with this. So in this case, what I do is I write T, then a column vector T naught absorption from different transient states to the absorbing state, and then a row vector, and then a zero. Therefore, this will be looking like, for the transient part, we have lambda 11, lambda 12, so on lambda 1m, lambda 21, 22, lambda 2m. Then it goes like that. Lambda m1, m2, lambda m. Then for this T naught, I just write, let me write that as say T1 naught, T2 naught, so on Tn naught. And then here, these are all zeros. Why zeros? Because it's a row vector, but then there should be some reasoning behind that. Now this part is our T matrix. This is our T matrix. This one. And then T naught is this. This is our zero vector, row vector. And this is the scalar zero. This is our this morning is the phase change represented. So in the representation, what we do is yes. So this is our alpha bar. Alpha bar is alpha 1, so on alpha n. Very often we take alpha n plus 1 to be equal to 0. The reason is it starts from the absorbing state permanently here. So there is nothing counter. And therefore, we assume that alpha n plus 1 is 0. That means it does not initially start from the absorbing state. Therefore, it starts from a transient state, stays in the transient state for a certain amount of time given by u, which is a random variable therefore. And this u is the convolution of a random number of non-identical exponentially distributed random variable. Non-identical because parameters will be changed, but then there may be some repetitions also. For example, the state 1 to 2 transition or 2 to 1 transitions may take place several times. And so this u will be, this random variable u will be convolution of, I call it like this, exponentially distributed random variables like this, xij, some, but then this is not actually a solution. Several times this I to j transition, j to a transitions can take place. Sometimes certain transitions may not even take place before absorption. So ultimately what happens is that there can be a very large number of this random variables. When we refer to that, you may become arbitrarily large. Because extensions are all exponentially distributed with parameter Xij is exponentially distributed with parameter lambda ij. Exponential lambda ij. So what is the mean of this? Means order time, expected time of Xij. This is equal to 1 by lambda ij. And then when I take the expectation of this u, if there are, this is an infinite series, it can happen that it's an infinite series. In this case, this becomes infinite. That's because these are all non-negligible terms. And therefore, this can become infinity. And therefore, absorption may take an infinitely long time. There comes an infinity. Now this is probably the working linear algebra. Let's speak about the invertibility or modic invertibility, but then I'm trying to give a probabilistic meaning for non-invertibility. Let us say, main purpose in that, just to introduce. Now, what happens is, along the diagonal, these are actually indicating it stays there itself, no change is taking place. And then if you write down the different equation, actually this we get when we write a system of different equations satisfied by the transition probabilities. That, say for example, suppose I write Pjt for the probability that at time t, I now use a notation x of t to designate the state of the process at time t. So xt equal to j under conditional. That means I am not speaking anything about the initial state. And then I write the different equations satisfied by the Pjt. So Pj dash t, for example, I have to write. So this is equal to, suppose it was in state j at time t, it was in state at time t, so that at this point of time, it is in state j. And then, in the short interval of duration t plus x, and there should be no change taking place because in a short interval, either no event or one event can take place with positive probability. So it should stay there itself. So no change. No change would mean that the parameter now is, for example, here, what are the things that can happen from 1 to, it can go to 2, 1 to m or get absorbed. But then what I am trying to find out is something like this. I am now looking at only the transient part and concerned only with the transient part, not concerned with. So what I am going to do is, how long it is going to stay within the transient state rather than getting out of the transient state. And therefore, I am interested only in the transient state and not the absorbing state. So it just stays there. Obviously, I will just consider this one. So since I am considering only the transient part, what I have is, it is not going out of J. But then, if it is restricted to the transient part, it will go up to M only. So the negative of that, I am going to write. Negative of that means the sum of these things, of course, this will also be included. So this will be the negative of the sum of the elements in the system. Similarly, these things are written. Along the diagonal we have negative. Why negative? Because you may ask why it is so. I should give actually answer to that question. So this is that from 1 to 2 it goes as probability for lambda 1 to x plus BT of x. And looking at all the mutually exclusive and exhaustive cases. The other possibility goes to 3 from 1. So x plus BT of x. And then later lambda 1 m x plus BT of x. And of course the absorption also finally figured. So then there is no change to mean that nothing of these won't happen. So what is, since these are the probabilities of mutually exclusive cases and exhaustive in the sense that when you are not considering this. So the probability that it does not move out of this will be, what is that we can say? So what will happen is, this is a moving out. So staying there, lambda 1x plus dp/x, that means it moves from 1 to 2 in the short duration. And therefore, what is the probability that it does not move out? It will be, if you just look at this one, you can see that it is 1 minus all these things. Lambda 1 2 plus 1, lambda 1 m, lambda 1 m plus 1. And this thing we designate as lambda 1 1. And this is a 1 minus, so since I write a different equation, I write Pj t plus h minus Pj t equal to Pj t. No change. You should be staying there. It's pulled up. Sorry. That's what I should know. Pj t plus h. At time t plus h, it is staying still at Pj. State j. So 1 minus no change. That means none of these things happen. So 1 minus lambda 1 2 h and so on. So lambda 1 n plus 1 h plus beta h. And then, of course, the other possibility is that because in some other state, I at time t, and then in the short interval, it is coming to, so this I can be anything transient, not a solid state. Transient, any one of the transient states, and then it comes to the absorbing state. So in the short interval, yes, this comes to, from I it moves to j, x plus b. This is how the difference equation comes. I had now some more I, but I am not equal to, no, they are not equal to I because j, I equal to j is not what we consider here. So variation for I from 1 to, right, m plus 1 will not be counted here because it is to stay in the transient state. And then I have to write j not equal to 1. Or I not equal to because we are fixing it. And then subtract this Pj from those sides. And then divide by Pj, take the limit as exclusive 0, you will get the differential. So that I write as Pj dash t equal to, that's how the negative things, the negative value appearing on the diagram. Pj dash t equal to minus, therefore I write just lambda 1 1. This because when writing Pj dash t, how it is coming? Because in the previous equation we subtracted Pj t plus h. Pj is subtracted from both sides. Therefore, this is minus of lambda 1 1, lambda 1 2 plus 1, lambda 1 n. So this part is whereas I need not have to consider this because otherwise, but then yes, that will be actually coming because it is lambda 1 1. That's all. So what happens is these things put together they are returned lambda. So subtracting this, we get P plus S minus PAT divided by S. Take the limit. And therefore we get S. So lambda 1 1. I should not now write the definition because it is now a non-positive quantity. So yes, these are actually we have already divided by that. So it goes lambda 1 1 PAT plus this. And then what happens? Collect all the coefficients. We write the differential equation, find a matrix differential equation. So if I use a notation like this, P T to stand for P1T so on P N T, this vector. But these are not only possibility because P n plus 1 I have not considered. And then it's a coordinate wise derivative. This is P1 dash T, P m dash T. Then what we are getting from these things is the matrix differential equation. P dash T equal to dt, and then we can notice that the coefficient matrix will be exactly this way. But then now we require the initial condition. The initial condition is P0 equal to alpha bar. Because initially it is occupying one of these states 1 to m. That's how it proceeds. And therefore the solution to this matrix differential equation will be, and that is how the phase space distribution is given. So this will be giving us P of T equal to e power alpha bar T, and then if you use the initial condition, now alpha bar, sorry, not alpha bar, sorry, this is wrong. Tt, e power Tt, T of T equal to alpha bar P, Pt, and then this is a Pro vector. So this is not exactly probabilities, it is a vector of probabilities, and therefore if you multiply on the right hand side by the quantum vector of ones of the same order as alpha bar, so the component wise probabilities we can up. You can write down the differential equation. Therefore, now this is the probability that absorption does not take place until time t, component wise. This is a vector. So probability of absorption takes place at or prior to time t. U less than or equal to t is the complement of this thing. This I am not multiplying at this point of time. This is a vector. Now this is therefore equal to complement would be that absorption takes place at or prior to time t. So 1 minus alpha bar e power tt into e bar. E is, or shall I write a different notation because E, this one and this should not be confused. So I write 1 with this. So this stands for quantum vector of ones of order n. So this is a row vector and then of order n, and then here because we can have the pair series expansion from this, and we get this. So this is therefore this part, this is taking the representation. The representation, this alpha and V are the ones required in the representation. Therefore, we call it phase-state representation with the representation alpha bar V of order M. These are the derivation is done. Now, one may ask a question. Suppose we have a random network. We have a network. There are several nodes, 1, 2, so on. Or a prisoner's problem. A prisoner is just getting the prison. There are M cells from M transient cells, that means he cannot escape. And there is one cell which is M plus 1, which is absorbing. That means once he gets into that, he is out of the prison. So he just moves randomly among these according to the rules I have created here. How much time or within a given t, what is the probability that he escapes at a private time t? Or you can just imagine a random network and then, or a random graph. Speak about this correctly, the character does. What is the probability that it's a character graph? But in what sense? Before getting absorbed into state n plus 1, what's the probability that all nodes are visited before absorption and within a given time? Or what is the probability that it just directly jumps into, say, starting from node I initially, it just directly jumps into n plus 1. Obviously, we know that this is a responsibility distributed, but there are several possibilities that we can think of. It can start from any one of the transient states and directly jump into n plus 1. And then for a connectedness, we can if cycle is permitted, then at the private time t, what is the probability of getting absorbed into this with the network completely connected? Probably without cycle. Without a cycle, then we have to think of the permutation. Without a cycle, would mean that we have to think of a random permutation of the coordinates 1 to m. So I1, I2, so on, IM. This is a permutation of these elements 1 to m. And then we have m plus 1. So think of an order like this, moving from I1 to I2, so on, IM. And then can have various rearrangements for this. So all such permutations take into consideration and then it gets absorbed. So that also can be computed in a single time. So this would mean that there is no cycle because each node is visited only once. So cycle will always form. So the probability for, you can ask any question to this one and that is the answer concerning the network. And then what is the probability of it taking an infinitely long duration? That means that number of transitions without there is 7 cycles. And therefore, as I indicated earlier, this x will be an infinite sum. So conversion of infinite for conversion of non-identical, but there will be identical distributed identical source. So you want this one. So I1 to Ij, I1 to A1, then this notation is not right. And just write Xij with a I not equal to j. But even then it is not complete. This notation is not complete because after this transition can go on indefinitely before getting absorbed. There will be this t for the time it absorbs this u the value, expected value of u equal to u. Because then defined number of transitions. So, for other questions, this will be answered. And in this quarter, typically I will give you a minimal phase tape representation. You know, what is the importance of minimal phase tape representation? So, for a given, the virtue of the property of the phase tape distribution that it is dense in the class of all distribution, so that the conditions involved are, you should be on the non-negative or the real line. So, there will be a larger number of phase tape distributions that can approximate a given distribution. But then, how close is this approximation? That's one question. And the second thing is that what is the minimal representation? So the representation, this M is a very important factor. For computational purposes, making this M and getting an optimal value is very important. It should not be very large because computationally there will be a lot of different elements. But then it should take into account all varying features of the distribution. So accordingly, this is, that's why we just use the word optimal. And then there should be a representation that will be minimal in the sense that optimal. If you bring in the operational principles also. Otherwise, just the minimal will be fine. What is a minimal representation? That means what is the one that can take care of all the varying features of the distribution and finally leading you to a phase approximation. The closest one. I am now going to give you a phase tape representation for the gamma random variable. If there is 10 or not? Say, energy. So gamma random variable है. The gamma random variable है. Okay, gamma p एंनुള്ളത് gamma integrated नहीं होगी. यानी अंगेरे अंगेरे statistics but statistics don't है. अरे define किया व्यत्यासन आएगी. अदिलोग नहीं so it is 0 to infinity e power minus d t power p minus 1 dt. So p should not be a negative integer. Should not be negative. But it is another candidate and probability density probability distribution. Because this gamma p would have the side. Suppose you divide both sides by gamma p. So this is 1 by gamma p integral 0 to infinity e power minus t power p minus 1 dt. This is equal to what? So the p says can be, when p is a positive integer, for example, it is equal to 1, p equal to 1. So gamma p equal to 1. 0 factorial which is 1. So you get the exponential distribution from that. So it will be, well, with the parameter, the lambda will be equal to 1. That's what it is. Exponential distribution, the parameter is when lambda e power minus lambda t dt. Integral 0 to infinity, and this is equal to 1. Now, in this one, Without the lambda, this will be just looking like p equal to, so p power t power 1 minus 1 0, this is equal to p equal to 1, and therefore p power 3 minus 1 is 1 minus 1 0. So this is the exponential. So we get that. Now the next stage is the Gardner density. Gardner of order k, that means IAD exponentials x1 plus 1 plus xk. What these are called IAD exponentials. IAD exponential with the same parameter, exponential lambda. So that is what is called the LR distribution. And we get this as equal to e power density, corresponding density is e power minus lambda t, lambda power k, t power k minus 1 by gamma k. The density corresponds to sigma of xi, where xi's are IAD exponential. This is what we get. So these all come as particular phase of phase shift distribution. That actually demonstrated in the morning. Now, this case I am considering only an integer value, the convergence of an integer value random variable, number of random variables. Integer value, integer k is a positive integer. That's what I meant by integer. Inside of this integer value, what will I do if I take p, where p is not an integer? There comes the starting point of representation of gamma as a base state. So I come to that. Suppose I take p equal to 10.3. It's a demonstration. So this means that the random variable, this sum, suppose I write x, so this is the sum of x1 plus x2 plus 1 plus x10, and then a fractional part of the same type of random variable. So I write the random variable y, which is independent of these random variables and identically distributed as the random variable for this random variable. And then I multiply this by a theta. But then this theta equal to 0.3. Now if you proceed in the way even was presented in the morning, you get the exact representations of the phase state. No, this gamma random variable, this particular gamma random variable, it will be something like minus lambda zeros. Oh no, usually this is not right. This will be lambda. Then minus lambda here, lambda minus lambda zeros. Before that, there is one more. Finally, I have theta lambda minus, this is minus theta lambda, and this is the phase state represented for the gamma random variable with the p equal to 10.3, where theta equal to 10.3. No, theta equal to 0.3. This, in fact, the medium exact representation. That is something that Viswanath, when he simulated, it was showing a minor deviation. It did not make so much of simulation that there are some agreement close enough. So this one, and then at the same time, they will expect something about this representation, something was not done. what I have done here. That is actually confirming that my result is correct. Yeah, that's all. But is there ശരിയാണല്ലോ അവിടെ കഴിയുന്നുണ്ട് but then let's not pose the question how you can try to represent a Dept distribution based on gamma. If that you can succeed, then this will be more closer because see this linear representation is still beginning to be an open problem. That may probably give some light, throw some light to that linear representation. With that, thank you for the patience. If you have some questions, I will try to answer.
If there is a presentation, we can
That's good.